Hello! Today we are talking about polarity. So before we begin, it's important that you remember that we have two different types of compounds. We have ionic compounds, which is a metal combined with a nonmetal. So in this case, what happens is the nonmetal has a higher attraction for the electrons. So the nonmetal is actually going to pull the electrons towards it off of the metal. Okay, so that has to do with an electronegativity difference. So the more electronegative nonmetal pulls the electrons off of the less electronegative metal. So if you remember from previously, electronegativity is kind of a way of measuring how strong of a magnet these atoms are. The higher the electronegativity, the stronger it pulls on electrons. Okay, so high electronegativity pulls the electrons, makes it fully positive because it gained negative electrons. So fully negative. Makes this one fully positive because it lost the electrons, lost the negative electrons, making it positive. So we call these ions. We also have covalent compounds. So the covalent compounds only involve nonmetals. There's no metals here. And they share the electrons. Now there's actually two different kinds of covalent compounds. There's polar covalent compounds, which involves an unequal sharing of the electrons. One of them kind of hogs the electrons more than the other. And then there's non-polar covalent, in which there's perfectly equal sharing. So here, it's kind of like you're playing tug of war with the electrons as the rope, and they're pulling exactly equally. Both sides of the tug of war pulling exactly equally. So yes, they're both pulling on the electrons, but the electrons aren't going anywhere. So they each get to count them exactly equally. And that results in no charges at all, which is kind of the complete opposite of here. Okay? And that is because the electronegativity difference is 0. They are the exact same strength. They pull the electrons equally. Polar is my in-between for these. It's not strong enough to fully pull electrons off, but there is still pulling. And that results in an unequal sharing of electrons. Okay, so in my example here, what we see is hydrogen bonded to chlorine. Okay? Now, these symbols here mean slightly. So I have a slightly positive and a slightly negative chlorine. Slightly positive hydrogen, slightly negative chlorine. Now, what I did is I looked up the electronegativities on the periodic table. So I looked up hydrogen, and it's actually just directly on the periodic table. Right here. So hydrogen's electronegativity is 2.2, and I looked up chlorine. Chlorine's electronegativity is 3.16. Okay. Now, if you notice the trend, fluorine actually has the highest out of everything, and it gets lower as we move away from fluorine. Okay. So, I looked up the electronegativities. Chlorine has a higher electronegativity. So it's a stronger magnet. It pulls these electrons that they're sharing, it pulls them closer to chlorine, kind of hogs them a bit. Okay? So that results in chlorine being slightly negative because it pulled the negative electrons towards it. And hydrogen's slightly positive because it kind of loses the electrons a bit. Chlorine gets to count them more. Leaves a positive void because the electrons kind of shift towards the chlorine. Okay? All right, so what does all this mean? Okay, so actually let's not look at that yet. All right, so this whole unit, solubility, is about if things dissolve or not. It's kind of the whole point of the unit. Are things going to dissolve or are they not? That's what solubility is. So polarity tells us a lot about that. So the term is like dissolves like. So what that means is that polar molecules will dissolve in polar substances. Polar will dissolve with polar. Like dissolves like. And nonpolar will dissolve with nonpolar. Okay, like dissolves like. So polar with polar, nonpolar with nonpolar. An example of this would be like if you've ever gotten butter on something, like a knife or your hands or whatever, butter. Okay, if you take that buttery knife and you try and put it under water and just rinse it off, nothing really happens. You cannot get the butter off the knife, like to save your life. Okay, and that's because butter is non-polar. There's no charges on it. And water is polar. So I'm trying to mix a non-polar with a polar, and that does not work. Okay, so that's why it's required that we use soap in that case, because soap's kind of cool. Soap has a polar end and a non-polar end. So soap kind of forces them to interact. Polar and non-polar can mix when we use soap. Okay. All right, so like dissolves like. That's kind of the whole concept here. And if you're just talking about two atoms, it's pretty straightforward. You just look up the numbers on the periodic table. The one with the higher number gets the slight negative. The one with the lower number gets the slight positive. And if the numbers are exactly the same, you won't even see these symbols because they're sharing equally. No positives or negatives. All right, but what if it's a molecule? It becomes a little bit different. And I pretty much just rely on this flowchart. It works pretty much all the time. Okay, so this is what I rely on all the time. Just two questions. So, are the atoms surrounding the central atom the same? And are there lone pairs on the central atom? Easiest thing to do to explain this is just to do a couple examples. So let's take a look at this molecule here. Okay, so going off of the first question, are the atoms surrounding the central atom the same? Okay, so here's my central atom. Are the atoms going around it the same? And literally all I mean is, are they the exact same atom? So I got hydrogen, 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 hydrogen. Yeah, those are all the same. Okay, so yes. Are there lone pairs on the central atom? Now what that means is, are there dots on the central atom? Okay, like this. So remember when we used to draw them, that just says that I have a pair of electrons that's not being shared. So do I see any dots on the central atom? Any dots here? No. Okay, I don't care if there's dots on the outside atom. Only care about the middle one. So no, there are no lone pairs on the central atom. This is nonpolar. Okay? And that's pretty much all you need to do for a nonpolar molecule. All right, let's look at another one. Let's look at this one. It's a little hard to tell with the bent on what your central atom is, but it is still this one. These guys are technically going around it. They're just bent downwards. So are the atoms surrounding the central atom the same? Are these atoms the same? Yes, they're both hydrogen, again. Are there lone pairs on the central atom? So does my middle atom have any dots on it? Yes, it does. So water is polar. Okay, so what does this actually mean? Well, it tells us that it will dissolve with other polar things. But the reason why is because I'm going to be able to draw a line somewhere in this atom and say, hey, on this side of the line, I have all slight positives, and on this side of the line, I have all slight negatives. Okay, so we'll do kind of just what we did with that other compound that we had a second ago. You'll look on the periodic table. Oxygen's electronegativity is 3.44. Hydrogen's electronegativity is 2.2. So oxygen has a higher electronegativity. Okay, so oxygen pulls the electrons towards it. Higher number, that's literally all I looked up. Bigger number here, smaller number here, pulls it towards it. Bigger number here, smaller number here, pulls it towards it. So oxygen hogs all the electrons, and that makes oxygen slightly negative. okay? And this hydrogen kind of loses the electrons. Not fully loses, but, kind of loses them. So that makes hydrogen slightly positive. Okay? Same thing here. Hydrogen kind of loses them, so slightly positive. Okay, this symbol here just means slightly. It's kind of like an 8 that you don't finish, or an S that you went a little too far on. All right, so see now I can draw this line. And I can say everything down here is slightly positive, everything up here is slightly negative. I have poles, just like a north and south pole. I have a negative side and I have a positive side. Okay? So this will cause it kind of to behave like a magnet. The negative side will attract positive things, and the positive side will attract negative things. It tells us a lot about why water behaves the way it does. Okay? Let's look at one more example. All right, so first question, are the atoms surrounding the central atom the same? So here's my central atom. I've got a chlorine, a hydrogen, a hydrogen, a hydrogen. Nope, those are not the same. One of these things is not like the other. Immediately it's polar. Which tells us this will dissolve with water. There are a couple exceptions to that rule, but we won't be too horribly concerned about them. Okay, so it tells us that it's polar. Now let's figure out where I can draw the line. And sometimes you don't even have to do that. Sometimes you can just be done by saying, yep, this is polar. It'll dissolve in something else polar, like water. It will not dissolve in non-polar things. Sometimes that's all you need to know. But if we need to draw the little slightlies, it's not too hard either. You just compare them. So I've got my chlorine and carbon. So chlorine has a 3.16. Carbon has a 2.55. So chlorine's number is bigger. Chlorine hogs the electrons away from carbon, making it slightly negative. Kind of ugly, sorry. And that makes the carbon slightly positive. Then I look here. Carbon was the 2.55. Hydrogen's 2.2. So carbon has the bigger number, so it pulls them off of hydrogen. So probably overall that'll change this from being slightly positive to slightly negative, but that really doesn't matter too much, so don't really overthink that. Definitely what it does to the hydrogens is it makes them slightly positives. And then I can draw a line somewhere in here and say slight negative side, slight positive side. Okay, so for example, if I was comparing this to the water, I could say, hey, this negative side attracts this positive side, and I'd have a force of attraction here. And that's why they're able to dissolve. Okay, and then this guy having no charges, that tells me that they can't dissolve. They're not going to mix. Okay? Now, truly, just to get a little more involved, you can see symbols on a nonpolar molecule. So if I compared carbon to hydrogen, carbon has the 2.55 and hydrogen has the 2.2. So it does what we kind of just showed. Okay, I have all the slight positives on the hydrogen and slight negative in the middle. But can I draw a line anywhere and say, hey, slight negatives on this side, slight positives on this side? You can't. Okay, so since that doesn't exist, there is no line where there's a positive side and a negative side, there's no poles, that makes this nonpolar. And it's not going to mix with these guys. So don't think just because you see the little slightlies, the little symbols, it's automatically polar. It really has to do with, can you draw the line or not? Okay? And as I said, the flowchart will tell you that. So you really just need to follow the flowchart. Be like polar or nonpolar. Like dissolves like. Polar dissolves with polar. Nonpolar dissolves with nonpolar.